So we are going to start the topic metric tensor. Metric tensor. So what is a metric tensor? Actually, the metric tensor is a function which tells us how to compute the distance between any 2 points in a given space. So let me write it here, or maybe I can copy paste it here. Let me write it. The metric tensor is a function which tells us how to compute the distance between any 2 points in a given space. Okay, this is the simplest example. It may not be the complete example, but this is the simplest example we have. So let us look at its expression. Okay. So in general curvilinear coordinates, so let me write it here. In general curvilinear coordinates, we have the displacement vector dr vector is equal to dou r by dou x1 dx1 plus dou r by dou x2 dx2 plus dou r by dou x3 dx3. Okay, this x2 have equal x square have and this means x3. So x1, x2, x3 are the 3 axes of the curvilinear coordinate system. Okay, in 4 dimensions, I'll add one more, that is dou r by dou x3 dx3. So, so for typing, let us keep it simple. Let us keep it simple. So this dou r1 by dou x1, this is represented. This can be represented by a vector, that is a1 vector. Okay, dx1 plus then second dou r by dou x2, we represent it by a2 vector dx2. The third, we represent it by a3 vector dx3. Okay, and we saw earlier that dx1, dx2, dx3, they are actually the contravariant components. They are the components of a contravariant vector. Manika, I repeat, dx1, dx2, dx3 are actually the components of a contravariant vector. And this a1 vector, a2 vector, a3 vector, these are the basis vectors. So a1 vector is a basis vector along the direction of the x1 axis. A2 vector is a basis vector along the direction of the x2 axis. A3 vector is a basis vector tangent to the x3 axis. And a1, a2, a3, these are basis vectors, but their magnitude may be greater than 1 or less than 1. So they are not unit vectors, but they are still basis vectors. Okay. So this is the displacement dr vector. Dr vector in general curvilinear coordinates, where x1, x2, x3 are the coordinate axes. Now, if we want to find out, I repeat, if we want to find out, so let me draw this 2 points here. So this is the first point P, this is the second point Q, and the displacement between them is dr. This is infinitesimal displacement. Okay. So PQ, that is the displacement, and dr. Okay. So the square of the element. So then the square of the element of arc length is, okay, this length, the square of the element of this length. So asang square se, it is given by ds square. This is equal to dr vector dot dr vector. Okay, it is given by dr vector dot dr vector. And then we substitute for dr vector. What is this? A1 dx1 plus A2 dx2 plus A3 dx3 dot A1 same dx1. Sorry, it should be superscript, not subscript. So let me remove this, undo. So A1 dx1 plus A2 dx2 plus A3 dx3. Okay, so this is the dot product of dr and dr. This is the definition of the square of the element of arc length. This, if I take the dot product, so this is first A1 dx1 dot product of A1 dx1. So what do we have here? A1 dot A1 and dx1 here. So it will be dx1 whole square. Next, I take the dot product of this with the second term. Okay, so this will be A1 dot A2 dx1 dx2. Okay, now I take the dot product of this in the third term. This will be A1 dot A3 dx1 dx3. Okay, then plus, now I'll take the second term and take its dot product with these three terms respectively. Similarly, I'll take the third term and take the dot product with these three terms respectively. Okay, so I'll add up all these terms. How many terms will be there in total? Term kya legani? There will be nine terms. Okay, very good. There will be 9 terms. So that means this expression. So all these 9 terms, I repeat, all these 9 terms, they can be written in a shorthand form. They can be written in a shorthand form. Let us do it. So we can write it as ds square equal to gij dxi dxj. They can be written in the shorthand like this. Now here we have 2 repeated indices. That is I, the index I is repeated. Similarly, the index j is repeated. So that means it actually means summation over I from 1 to 3. And similarly, summation over j from 1 to 3. This is gij dxi dxj. So this is contraction in the index I as well as contraction in the index j. And here we have used the Einstein summation convention. Okay. So what is G here? G is actually Gij. This is actually AI dot AJ. This is the dot product of the basis vectors AI and AJ. What is AI? AI is the basis vector along x1 axis. AJ is the basis vector along x2 axis. Okay, so their dot product is Gij. And since dot product is symmetric, we have GJI. So GJI means AJ dot AI. And since dot product is symmetric, this is simply equal to AI dot AJ. So this is nothing but Gij. So this quantity Gij, which we have defined here, it is symmetric about the two indices I and j. This is simply a property of the dot product. Okay. So far, so good. So everything is clear till here. Yarba?
Yes, sir.
Okay. So let me write this again. So ds square equal to Gij dxi dxj. Okay, this is called the line element. This is also called the line element. Okay, and this gives the square of the distance between 2 points separated by a displacement dr, and dxi are the components of those of that displacement di. And this Gij, the term which we have introduced here, this is actually the component of the metric tensor. Okay, this Gij, it actually turns out to be a tensor of rank 2, and we call this tensor metric tensor. And how do we know it is a tensor? Here, look at this expression, the left hand side, ds square, it is a scalar. Okay, it is it is a scalar quantity. Scalar means tensor of rank 0. So it is a tensor quantity. dxi is a contravariant vector. dxj is again a contravariant vector. So if we apply the quotient rule, so Gij then should be a tensor. Okay. Now dxi multiplied by dxj, the outer product of two contravariant vectors, this product is actually a contravariant vector of rank 2. Okay, so this is a contravariant vector of rank 2. It gives a vector, a tensor. Sorry. This is not a vector of rank 2. This is a tensor of rank 2. Vector of rank 2, highway are tensor of rank 2. So dxi multiplied by dxj is a contravariant tensor of rank 2. Okay. And similarly, ds square, it is a tensor of rank 0. That means this is a tensor of rank 2, and it is a covariant tensor. So Gij is a second rank covariant tensor. And this is known as the metric tensor. Gij is actually the components of the metric tensor. And the elements of this tensor, if they are written in a matrix form, they can be written in a matrix form. This Gij, the elements of this metric tensor can be written in a square matrix form. So in 3 dimensions, this will be a 3 by 3 square matrix. Okay. So as I said, this Gij can be written as a square matrix. Okay. So if this Gij is written, if the elements of this metric tensor is written as a square matrix, then we can take the inverse of this square matrix. See, square matrix inverse. We can take the inverse of this square matrix, and the elements of those inverse matrix are written as G contravariant Ij. So this is the inverse matrix.